Welcome back. Let's start with the upcoming session concerning results of algebraic geometry which do not relativize well. Let me explain in the first section on motivation on what I mean by that precisely. So first we notice that we have two facts, and the first one concerns synthetic algebraic geometry. In synthetic algebraic geometry, everything is stable under pull effect. There are several things what I could mean by this slogan. For concreteness, let's have a look at one way to make that precise. For every base scheme S, if a statement phi holds in the big Zariski topos of that base scheme, then also this holds for all schemes X over S. By scheme over S, I mean a scheme together with a morphism to S, and that morphism should be locally of finite presentation, LFP. And by Zariski topos for completeness right now, I mean the only version of the Zariski topos for which I am intimately familiar with how it's actually built and works. So I mean the one categorical Zariski. Okay, and that is not a deep statement if one is familiar with certain basics of categorical logic, because this Zariski topos is simply a certain slice, namely over the function of points of X of the original Zariski topos. And it's a basic result in categorical logic that if a statement holds, then it also holds on all later stages. So that's a fact about synthetic algebraic geometry. And now I'd like to compare that with traditional algebraic geometry. In traditional algebraic geometry, there are results which don't relativize. In fact, there are many such results. Let me just mention two. For instance, we have the statement that every map, morphism of schemes, from A1 to A1 can be extended to a map from A1 to B1. We will study that particular example in more detail very soon. So we have this statement, and this does not hold for all base schemes S. There's a certain class of base schemes for which this holds. I don't know the most general description of that class, but one important special case, which you often read about in textbooks, is the following: is if S is the spectrum of a geometric field. So discrete field. Another is the following. Every vector bundle on AN is trivial. So by definition, a vector bundle is locally trivial, and it's a non-trivial statement that it is indeed globally trivial. This is an algebraic version of a familiar fact in differential geometry, that R to the n is not interesting from a point of view of studying vector bundles of it, because every vector bundle on R to the n is globally trivial, and that's an algebraic version of that. And this also holds in case that S is a spectrum of a geometric field. Yeah.
What about every vector bundle on the point is trivial, whereby the point, I mean the point over S or S itself?
Yeah, very nice additional.
So that's n equals 0.
Yeah, that's n equals 0, and that's true in case n is the spectrum of a field.
And not true in general.
Yeah, right. Right, because there are some over some rings, there are modules which are projective and finitely generated, which are not free. For instance, Z adjoint square root of minus 1. Yeah, so your example would be like a baby version of this one. And by the way, this statement here has a well-known name. It's I forgot it right now. It's Quillensystem, right? Quillensystem? Yeah, right. And so in full generality, it's a hard theorem. Nowadays, we know proofs which are not that hard and not that long. For instance, you find a proof in the textbook on constructive commutative algebra by Henri and Quitté. But originally, that was quite a difficult theorem, and history progressed along special cases. Yeah, just want to point that out.
But I mean, here you ask the question whether it's trivial absolutely.
Mm-hmm.
So, I mean, we could also ask whether it's trivially relative to something that comes from S.
All right, yeah.
And I think maybe this, I would say this is a more natural question.
I agree.
And then Matthias, n equals 0 example would
Right.
work always, of course. Because,
Exactly, yeah.
Yeah.
Yeah, I completely agree.
And do you know if the more general n is still a good example in the sense that it depends on S?
Yeah, I'm quite sure that it's even the better formulation, just proposed by Mark, is false for arbitrary S. I think there's a counterexample on that one.
For n equals 0 in arbitrary S?
No, not for n equals 0. For n equals 0, it's a trivial statement then.
Okay, yeah.
But for n at least 2, if I remember correctly, and perhaps even n equals 1, it becomes false as stated, and also false with the correction proposed by.
Can you explain the correction? So what does it mean come from S?
Yeah, there are several things what you could mean by that, but roughly speaking, I mean, S might also have vector bundles, and you can pull back a vector bundle living on S to one living on the F space. And now you somehow picture these as model vector bundles, which you still allow in your definition of globally trivial, even though it's not globally trivial, but comes from below. If you want to make that more precise, then one way of doing that might be to turn your attention to the Picard function, which, however, is not Zariski sheaf, right? So you have to sheafify, and I got lost in the details.
So there was this, if on the left hand side you take phi, saying that something is a weakly quasi-coherent module, you
Yeah.
seem to have a counterexample for the left hand statement, or not?
No,
No? Okay.
no. This holds in complete generality, and in particular, if in the Zariski topos of S, we know that some thing defined in here is weakly quasi-coherent, then we also know this.
The other thing was descent, so the other way. So if you have a cover of S by X.
But that would also hold. So this is if and only if, in case you would change the right hand side to mean that. So right now it's also if and only if for the trivial case, for the trivial reason that S is also an LFT scheme over S. Okay, but you could also say, well, there should be a covering of S by SIs as a risky covering. And then if you have that for all the SIs, then you are justified in including it for S. That also holds, including for WPC and including for everything else, what you can formulate here, which is at least things in one in the one categorical internal language of one topos. And then you can try to extend this to the hot situation, about which I'm unsure on the technical details. Or what is that counterexample you had in mind?
Yes, or you explained a bit what this weakly quasi-coherent means, and you said it does not mean stable, no pullback. That's how
yeah, but I
did it in my head, but probably
I didn't explain it as well. I think it's better to explain it later at some unspecified time instead of writing it down. The point is that these are at odds to each other. Here we have some kinds of restrictions, some kind of restriction on the base. And here I'm stating that everything is stable under base change. I'm not claiming that there is a precise relationship between the left-hand side and the right-hand side, but I did not give you that precise relationship. But still, I think you see that they are somehow at odds with each other. And the question is, how can we reconcile those two antipodes? And that was open for quite some time, till I think the last installment of this workshop. Okay. Let's have a look at this statement from traditional algebraic geometry in more detail, because it's an example which is not too hard, but also not too easy. So it's nicely fits the purpose of a test case. How do I picture this situation? We have A1 without 0, and we have A1, and we could have a map, for instance, a map like this, intuitively speaking right now. Then observe that this scheme embeds into all of the affine line, and observe that A1 embeds into P1 by mapping an element U to U colon 1. Yeah, and the question is there an extension like that? And if you have never thought about that, then this might look like a random question, but from the purpose of how P1 is often motivated, this is in fact a very basic question, because under this correspondence, this gets mapped to first f of x by x to the n colon 1. But then notice that we might also be able to reformulate this as follows. And now we might at least hope that this map is now well defined for all x's, including x equals 0, which was omitted from the domain before. Because at least we are no longer obviously dividing by x or some power of x. Okay, that is a hope which you might have.
So you can say that again. So I can send my x there.
Mm-hmm.
Okay, now I did.
And your hope is
I want to make it work for x to 0.
right. And you might hope that this is a good definition for the looked for extension.
Right. Okay. And just right. In case I knew that f of x, excuse me, that f of 0 was invertible, non-zero, then we are completely fine, right? I can write exactly this. Right.
This whole so this particular definition is a well-defined definition, and indeed gives us an extension in case we know the following. if for every x we know that x is not 0 or f of x is not 0. And with a little bit of classical logic, you can approximately rephrase that to if f of 0 is not 0. Classically and traditionally or informally speaking, vaguely speaking.
I think it's also formally true in SAG. If f of 0 is invertible, then E of f is an open.
Yeah.
That and the union of D of f and D of x is 1. No, am I mistaken?
So how do you prove the direction from bottom to top? Given an arbitrary x, how do you find out whether x is invertible? X is invertible.
Okay. Yeah, maybe not. Yeah. Okay.
I mean, it can't work because I mean, follow this example.
Because they are counterexamples, yeah.
So okay, wait. So the point is not that we want this to work for every f. We're completely happy if we can make it work for f where f of 0 is not 0.
Well, the result in traditional algebraic geometry is at least over the spectrum of a field. Every map whatsoever can be extended.
Yeah.
Every map whatsoever. So in the end, we should not need to put some condition on f. Not this one and not this one and no condition, no other condition.
So we can't say that it can't work.
No. The point is, I mean, the point is now when you add a parameter to this f, then you cannot continuously decide between going back.
Yeah, okay. Except if we know that for all parameter values if 0 is not 0, then I know not to make my decision. Right?
Yeah.
Okay.
I will write exactly this example on the board. In synthetic algebraic geometry, we have the following. For every number a, the map this map here, sorry, A1. And we extend it to a map from A1 P1. If and only if A equals 0 or A does not equal 0. Let's check parts of this proposition, namely that from this condition, the extendability follows. And let's first tackle the case that A is not 0, so invertible. Okay, in this case, we can do exactly this kind of trick and it will just work. The extension will be x goes to A colon x. And the picture that we have for this situation is the following. So how does that map A mod A over X look like? Depending on A, it might look like this, or it might look like this, or it might look like this. But in all cases, we can extend it to a map on the origin, and also on the origin, by mapping 0 to infinity. Yeah, to the point A colon 0, which is the same point as 1 colon 0, which is the reference infinity in P1. Okay. And also, in that other case, there we also have an extension. In this case, the extension is simply this one. So that we may not use the same term, because for x equals 0, both components would be 0, and that is forbidden for points of the projective line. Okay, hence I picked this other example, and this works. What's the picture for that? Well, how does the function look like? It looks like this. It's 0 here. There it's not defined, and then it's 0 again. Yeah, and one way to extend it is to just fill it with a 0 here. No need to go to the infinity, which would be available in P. Also recall that, yeah.
I think I can clear this up.
Yeah.
I think it works because
This one,
if
yeah.
I know that f of 0 is non-zero,
Yeah.
then I know for every x that the vector x comma f of x is not the 0 vector. And
Because if both were 0,
then x is 0 and also f of x is 0.
Yeah.
But f of 0 is not 0.
nice.
So it follows that x is not 0 or f of x is not 0 as we wanted.
Very nice. So by your observation, this here is a valid if and only if in the setting of syntactic algebraic geometry. But I am not claiming that from the extendability of this map, that follows. That would be false for the trivial reason that f of x might have x as a factor. Yeah, that the n is not minimal, so to speak. That I forgot to cancel or appearing x's.
0 is 0.
Yeah. Also recall in syntactic algebraic geometry, it is not the case that every number is 0 or not 0. And combining those two results, we see that in syntactic algebraic geometry, we cannot naively recover that theorem from traditional algebraic geometry.
What about nilpotent A? If I look at this picture, I have something which looks optically like it might be extendable. Because I don't go to infinity.
Yeah, right.
Something nilpotent divided by x. Well, but it still goes up, right?
It still goes up,
Yeah.
but it can't go up
For long, yeah.
to any
really
distance from 0.
Yeah.
So,
Exactly.
Yeah.
so according to pictures, it should be extendable.
Yes, I agree. I like your comment.
But that's exactly the point, right? You don't know that a equals 0 or a is non-zero in this case. In the case you're mentioning.
Yeah.
But I mean, we still have not for all A and R, or not A equals 0 or A equals 0.
Yeah, right. But so I did not mean this proposition as a joke. So this is indeed an if and only if. So you see that only the trivial nilpotent works, and then the invertible elements work.
Yeah. Okay, so there is some reason why it doesn't.
Yeah, yeah. I agree that it's not immediately clear from the pictures for me.
I think we can draw one more picture here.
Yeah.
I mean, which just gives a nice family of these maps where we cannot extend classically for obvious reasons. And so maybe you can
go ahead.
picture. So it's like proof of all this without words. Then we can. Okay, so this here should explain everything. Well, what do we see here? Well, in this direction, we have A1 without 0. In this direction, we have A1. So it's a family of A1s. And we see a map from A1 without 0 to A1. Namely, we map. So this is our parameter on each slice here. We map this point to the line going through the origin at this point. And as we never get this line, we stay away from the point at infinity in the P1. So this here defines a family of maps from A1 to 0.
From to A1 without 0.
0 to A1. And now the question is, can we complete these to A1 sitting inside P1? I mean, if you want to see the image A1, then it's here. And we just take the projection.
Okay.
And now we want to complete this map to A1. We can do it for every single parameter here. Because when we are this, so I mean, say if we are this parameter here, then of course we just map this point to the line, to the point in infinity in this P1. Mm-hmm. But there's a difference when we are at the 0 parameter, because in this case, I mean, everything is mapped to 0 at A1.
Or we take the horizontal.
Yes, and okay, now it's clear that we cannot. I mean, classically, and in the SAG, of course, as well, we can't extend this to A1 times A1 to P1.
Even if we start out with the base S equals a field, then the Zariski topos also incorporates non-trivial things, and then we could end up in this situation even if we did not intend it from the outset. Okay, so let me first write a summary and then raise the question again. The summary is that in syntactic algebraic geometry, it's not the case that every map can be extended. It is not the case that every map from A1 without 0 to A1 is extended.
And it also shows that the naive lifting criterion for completeness cannot work.
Exactly, exactly. Which is how we arrived at these considerations. Yeah. Okay, so let's observe the following. At first, this is like a sad state of affairs because in syntactic algebraic geometry, we endeavor to mimic all of classical algebraic geometry. This would be a fact from classical algebraic geometry, and we cannot mimic it. Okay. So how to fix it? There are two possibilities. One is not so good, and the second is the one which I advocate for. The one which is not so good is to drop the big Zariski topos and instead work with the small Zariski topos of the base. In that case, we still have that all results are stable under base change, but now the base changes are much more restricted because the base changes are only to smaller opens. So we are remaining on the same scheme we started with. And if that scheme we started with was the spectrum of a field, then we will always remain there. If it was the disjoint union of the spectrum of one field each, then we might zoom into one or the other component, but it would still work. We are no longer in a situation that that base changes to mostly arbitrary schemes of S are possible. So that's one option. However, we are then also leaving the realm of syntactic algebraic geometry. We are then in the realm of the more basic version of using the internal language of properties in algebraic geometry, namely just for the purposes of simplifying sheaf theoretic linear algebra to non-sheaf theoretic linear algebra. That's a nice simplification, but it's not of the same scope as those infinitesimals and the syntactic quasi-covariance and so on. All the nice results which by now we have obtained in syntactic algebraic geometry don't work, and it's really so there's a second solution, and let me present that one first in this ad hoc example, and then let's see what to make from that. So let me, just for the time being, amend syntactic algebraic geometry by one additional axiom. Later on, I will drop that axiom again. In the theory obtained from syntactic algebraic geometry by adjoining the axiom that R is discrete. So exactly the statement that every number is 0 or not 0.
So this theory is inconsistent.
Yeah. There, we have.
Doesn't matter so much what you write now.
We do have this tenability result.
Okay.
Proof?
I thought you would say something about Santa Claus, but no.
No. So I think you can follow along, even though this series is inconsistent, because I will not use the law of exclusion in order to carry out my proof. But in case you want to follow along more closely, then picture that I wrote something else before the comma, namely picture that I would have written in a certain subtopos of the big Zariski topos of the base scheme, namely the largest subtopos where R is discrete. But they are this holds. But we'll get to that anyway in a second. I just want to get under the proof. Okay, so how do we do it? Let F be an arbitrary map from A1 without 0 to A1.
Is there like a subtopos where R is discrete?
Yeah, discrete in the sense every element is 0 or invertible.
Oh, okay, great. Yeah.
That's what it is. Yeah. Let an arbitrary map be given. Then there is a unique. Let's get rid of the unique. Then there's a polynomial capital F in Rx and a number, natural number n, such that for x in R without 0, f of x equals capital F of x for x to the n. This is an application of, I think, syntactic quasi-coherence. Because that's not some arbitrary type. Instead, it's the spectrum of this polynomial ring localized away from the monomial x. Okay, and then by discreteness, we can carry out the following case distinction. By discreteness, we have that f of 0 is 0 or f of 0 is invertible. Okay, in the second case, we can write down an extension exactly as we already talked about before. An extension is given by the map x to f of x colon x to the n. And in the first case, the polynomial f can be written as x times some further polynomial g. And then we can continue by induction with g in place of f, the upper bound on the degree of G will be smaller than the upper bound on the degree of F. So this will terminate. Okay, that's the idea. And now the question is what to make of this proof. Right now, it's at least if we are reading this, if we're taking this seriously, I work in theory. So it's unclear what the purpose of the proof is, but let me explain. So a modal approach let's start with a definition. In the context of synthetic algebraic geometry, without any inconsistent additional axioms, let P be a proposition then consider the following proposition inductively generated by certain clauses. Then nabla P is the proposition inductively generated by the following clauses. The first clause is if P, then nabla P. So nabla P will be a certain weakening of P, similar to the double negation of P. But this is a less blunt weakening of the double negation.
What does it mean that you always have nabla P to double negation of P?
Exactly. But not the other way around. So that nabla P contains much more information than the double negation. And the second clause is the following. That's not actually one clause, but it's a collection of clauses. One clause for each element X in R. Namely, this here. So by this clause, we are justified in concluding nabla P, assuming that we can conclude nabla P under either of the additional assumptions X equals 0 or X. And sometimes we will also want a third clause, depending on the application. The third clause would be one clause for each polynomial f, which is monic and of positive degree. namely if f if this and this. In case you are not familiar with this kind of inductive generation, let me give an explicit description of NAPLA-P. I just want to do one example first.
Sorry, one question.
Yeah.
This NAPLA-P is then double negated, so this you can conclude. Or what was?
Yeah, so this is a lemma.
Yeah.
NAPLA, for every proposition P, NAPLA-P implies double negation of P in the context of synthetic algebraic geometry. Here's an example. In synthetic algebraic geometry, we don't have that R is discrete, but we have the following substitute. For all x, NAPLA is the case that x is 0 or x is not 0. Whether I write not 0 or invertible totally doesn't matter. They are equivalent in synthetic algebraic geometry. The reason is because I can conclude that by the second clause, because assuming x equals 0, I am able to verify this proposition. And also assuming that x is not 0, I will also be able to verify that proposition. So I need to apply clause 2 one time and clause 1 2 times in order to give a full proof of this example. Matthias?
So we're looking at these, so intuitively, I guess we are looking at these propositions that were that for once, if I have an x, I look at the proposition x equals 0 or x not equals 0, and then for every f in Rx, I look at this proposition that there is a 0 over there. And NAPLA-P is the nullification modality of this family of propositions applied to P, is that right? You're not sure that should be?
Yeah.
Okay, good. So, okay.
Yeah, and clause 3 means because we know that it should happen.
Yeah.
0.
We are kind of expecting that it has one.
But so now I would like to write down that NAPLA exists with 0.
Yeah, we're the same lesson thing, right?
Yeah.
Yeah, we have this.
So yeah, so this is the minimal way to force these two statements being true.
Exactly, something like this. I will write down in a second. Yeah. Recall. When you first learn constructive mathematics, then you are surprised that certain laws of classical logic do not longer hold. For instance, law of Lumidal doesn't hold any longer. Several versions of De Morgan's laws don't hold any longer, and so on. And then over time, you grow accustomed to that fact because you learn that, well, in constructive mathematics, those two logical connectives have a slightly different meaning. They have a stronger meaning. To verify a disjunction, it's not enough to just show that none of the two alternatives can fail. It's that you need to positive evidence for one of those. Recall all of that. And then also recall that there's a way in constructive mathematics to recover the classical meanings of those two connectives by defining the following. The classical existential quantifier can be recovered within the context of constructive mathematics by defining that as the double negation of the constructively meaningful existential quantifier. And also recall the same for the disjunction. So alpha or beta, the classical disjunction, can be defined as the double negation of the constructive disjunction. And then we indeed have results like that we have alpha or not alpha. This will hold in constructive mathematics. Or we will have the De Morgan rules, all of them, with that to the CL all over the place. Okay, so that's a way of importing classical mathematics into constructive mathematics. We just need to use those classical variants of those two connectives, and they are obtained by their constructive cousins by adding a double negation at the front. Here, with that modality, we are doing something very much related, with just one difference. Namely, we are not trying to force things to be classical again. Instead, we are trying to force R to be discrete. Yeah.
You just said modality, but you did not mean it in the sense we had before, the modality model type theory.
Right.
Something more restrictive when you only talk about propositions, right?
Yeah. I mean it right now in the following sense. I mean in that sense.
And implicit in what you're writing is that nabla is a map from propositions to propositions.
Exactly. And I propose from propositions to propositions, not from all types to all types.
But is there a modality of the universe of propositions?
Yeah, I think he means the nullification modality of these propositions above. And right, you said this inductive generated stuff here because it's for propositions simpler than for the arbitrary nullification modality, right? The arbitrary nullification modality we need high inductive type, that is maybe a bit complicated, but here it was easier.
Yeah, exactly.
Okay, what about D? With the formulation of the for all? Is this not true, or
Which
I mean, I would expect
you want an infinitary generalization of that?
Yeah,
If
but
I down,
internally.
cross it out because it will not hold.
Okay, yeah.
You would like
Right, yeah.
you would like something like this. And we don't have that, and we don't want that. It's not part of the definition of modality in this situation. We just have the direction from left to right, but not from right to left.
Because otherwise we would be able to prove in the example that nabla for all x and r.
Exactly. If I had this one, very nice observation. If I had this one, and if I trust that what I wrote there is correct, then I would be able to move the nabla to the front. And then we would have nabla bottom. And that would bottom, because it's just the fact that for all, that the statement that R is discrete, which we would have there if the nabla was put out of the way. It's just a fact that this is that the resulting statement would be equivalent to bottom. And then we would have nabla bottom, so not bottom, so bottom. So I would have written down a false statement, which I didn't intend to do. I wanted to write down an example. Okay, for those of you who are not familiar with that business of inductive definitions, let me give you an alternative description of NABLA-P. NABLA-P is equivalent to the following, namely to the statement that for all propositions Q, omega is the type of all propositions. We have the following. In the end, we will have this. And here I will write down P implies Q, and I will write down for X, if X equals 0, then Q, and also if X is not 0, implies Q. And then if you want to, then also a third clause, yeah? Depending on whether we want to have that as part of our definition or not. So this expresses that NABLA-P is the smallest proposition, yeah, intersection over all, such that P implies the proposition, and so that that proposition is stable under assuming one or the other alternative for the question whether X is 0. Okay, and yeah, with that model language at hand, we can recover, I will explain how, we can recover the result from traditional algebraic geometry. We can then have a look at what we have actually proven by having a look at what this amounts to in using our canonical model. And we can also, I will also write down a remark for simplifying work with those modalities. Okay, so firstly, what is the correct result in syntactic algebraic geometry? In syntactic algebraic geometry, we have the following. For every net F from A1 without 0 to A1, NABLA, there is an extension from A1 to P1. Okay. If you dislike those parentheses, you can also rewrite this as NABLA locally there is. Just as we sometimes say Zariski locally or FPF locally, we say NABLA locally. Why do we have that? Why do we have this proposition? How can we prove it? Well, we take the proof from earlier, which I think was at some point on this board down here. That proof was a fine proof, with the exception that it appealed to discreteness, which we don't have. However, NABLA locally, we have a good replacement for discreteness, namely this statement. Yeah. And yeah, this allows us to finish the proof. We don't actually have the case distinction whether P of 0 is 0 or invertible, but we have it under a NABLA, and then we can continue reasoning. It's just that we will be forever trapped in the NABLA monad, which is why we still have that here. And we cannot escape from the NABLA monad in general. We could escape to the double negation monad, and thereby forget even more information. But let's not forget even more information. Let's state the precise result. What's a corollary of this proposition? A corollary in or for traditional algebraic geometry. It's the following. So I'm not only claiming that what I will write down here is true, I'm also claiming that it directly follows from this result in syntactic algebraic geometry. in traditional algebraic geometry, for every base scheme whatsoever, even if it's not the spectrum of a geometric field, and for every map from A1 to P1 for A1 there's a covering of S. I will explain which kinds of coverings are acceptable for that. By its eyes, such that for each eye, there is an extension from A1 to E1 over the slightly smaller base Si. And which kind of coverings are allowed? So firstly, open coverings, so risky open coverings, the usual kind of coverings. But even more coverings are now allowed, namely the following ones, namely saying S is G of F together with V of F. Yeah, so that's in classical, traditional algebraic geometry, this is a true statement on the level of points. However, V of F is not open, it's a closed subset. This can also be made sense of in constructed traditional algebraic geometry, which I was using as my meta theory. And yeah, but in any case, it's a kind of covering which goes beyond the risky coverings. What this can amount to in practice is that, for instance, we exclude one single point where the extension would be problematic, where we wouldn't have a continuous extension over that point, as we have seen in the example from before.
Did you say what this topology is called?
This specific topology does not have a name as far as I know. Perhaps it's the I think it's very much related to, and perhaps the same one would need to check big topos, small topos, things like that. But it's related to the so-called flat topology, not the FPF flat topology, or to the patch topology or the constructible topology. And Peter has been nodding at constructible topology,
yeah.
so perhaps it's that one. Yes. Yeah.
And why do you say that one can make sense of the second, or the union of DF and VF? I mean, we don't have to, do we?
No, we don't have to. Just in case you want to make sense of that, you can, but you don't have to. Of course, when defining what a covering is, we can just write our preferred coverings. Ingo had a question?
You can compose them, right?
Yes, yeah, and arbitrary compositions of those. Yeah.
Yeah, so then I have so here you don't model the clause number 3. Just you use nabla with clause 1 and 2, right?
Yes, yeah, just for 1 and 2, right? If I would also include clause number 3, then I would need to add one additional kind of covering, namely the following one. Namely the covering, so now let's use Grothendieck notation for coverings instead of this subtheoretic notation. Namely, how is it usually written? Yeah, I think this V of F, like that, for every monic polynomial of positive degree. So that's covering not by 2 members, but by a single member And yeah, this is exactly the universal way of adjoining a root to S.
So if you just take 1 and 3, is it related to the FPPF topology?
Yes, it's very much related to it. And it's an open question of whether it's exactly the same. And if you have 1, 2, and 3, then the resulting coverings have a traditional name in traditional algebraic geometry, because these are then the coverings of the so-called surjective topology. Okay, there will be just one final comment in this talk. Let me summarize right now. So how did we recover that result from traditional algebraic geometry? We did not recover that by somehow sticking to our initial base, as we would have done if we went the little Zariski route. Instead, we generalized the coverings so that yeah, we don't notice that the scheme S may be getting more complex when somebody is doing base changes without telling us. Because we now are allowed to work with exactly those kind of coverings which we need in order to have that analog of the schemes. Okay, just the final comment is, how can we more easily work with that modality? I can imagine that when you first read this proposition, that you felt perhaps a little bit uneasy actually proving that. Like, I think believing that should be doable, but like actually proving that from this result and the laws for a modality might seem a little bit cumbersome. And luckily, there's a meta theorem which allows you to get rid of some of the work involved. That's the following. So now I put the nabla to the top. I did not put it on the front. Let me explain a second, but let me also say the following. For geometric formulas, phi, we have nabla phi is equivalent phi to the nabla. Okay, so in this situation, at least, there will be no difference between those two expressions. Recall what's a geometric formula? It's a formula made up of only the following constituents, top, bottom, and or existential, if you want to, then an infinitary disjunction and also equality, but no for all and no negation. The formula. And let me explain what this phi to the nabla is. That's the same formula as phi, but every existential quantifier is prefixed with a nabla, and every disjunction is prefixed with a nabla, and every equality is prefixed with a nabla, and every bottom is prefixed with a nabla. So you put nablas in front of all co-limit and equalizer things, yeah? So it's the same as nabla, but instead of the existential, we have nabla existential. Instead of disjunction, we have nabla. of the disjunction, and instead of equality, we have nabla of the equality, and this. Yeah, sorry, same as phi, right? And then the final clause, instead of bottom, we have nabla bottom. This is called the doubler translation. It's very similar to the more known double negation translation, where we would put double negations instead of nablas everywhere. In fact, for exactly the nabla we have here, we don't need to do this substitution, and I'm unsure right now about this one, but we definitely need to do these two. And for general modalities, we need to do all four. And yeah, with that explanation, you already see that this claim up here is correct, because, well, what is the nabla translation? The nabla translation would ask us to put the nabla in front of this disjunction, and then we just recover what was originally somewhere up there, I think. Yeah, that's the statement that R is nabla locally discrete. And why is that useful? It's useful because of the final bullet point in this remark, namely final bullet point, namely if in constructive logic you can show that phi entails psi, then we may conclude that phi to the nabla entails psi to the nabla. What does this amount to in practice? That means you can do the following. You ignore all of that explicit nabla computation business, and you just do your proof, but you use as an additional axiom that R is discrete. Then you obtain some conclusion. And then you just need to know that before, like, you publish your paper, you need to know that in actual fact, you have only proven the nabla translation of your claim, which in some cases you can simplify a little bit, for instance, thanks to that bullet point. And that is how you immediately obtain this proposition from that naive proof from before. I ignore all technicalities. I just do a proof using the X assumption that R is discrete. And in the end, I just need to recall that I need to translate the claim I've proven. This is why this nabla weasels in. And then that will be the result.
Matthias now proves 1 equals 0.
Mm-hmm.
So he has proven 1 equals 0 nabla translation of that.
Yeah. You're raising a good point. It's
yeah,
the same.
Yeah.
It's the same.
Yeah, because one is not.
Yeah. There's one subtlety which I'm missing currently.
I think you can only use finite. You can use x equals 0 or x invertible for a finite number of x.
Yes, exactly.
Yeah, but what does it mean then when you say you can do a proof anything?
Yeah.
But you cannot assume that for all x being 0 or x invertible. So
yes, but I was just claiming that you can do that.
You just claimed that you can use x. Okay, internal or external. This was not clear in your.
I was claiming that you can just. So it's not true. If the nabla from here is put to there, then we obtain a false statement.
Yeah.
So this statement is something which I never claimed. However, right now I was claiming that you can just ignore the technicalities and just assume that R is discrete in this sense. So with the universal quantifier. And now we are at an important issue, because if we interpret everything exactly as I said, then we can obtain bottom. And the way
But
out.
what did you write? Phi and test psi, then also phi number and test psi number. And what was your connection to this? Did you mean to say I plug in for phi that R is discrete, or what is phi?
For instance, it can be anything. I just wanted to point out that the number translation is sound with respect to intuitionistic logic. Intuitionistic predicate logic.
Yeah. But why can you make an assumption like you can make an assumption like x is 0 or x is invertible because the number translation of this is true.
Yeah.
Okay, but the number translation of for all x in R, x is 0 or x is invertible is not true.
It's also true, because the number translation of what you just said is this statement with the number there.
Yeah, right.
And
The number translation is true, but not number applied to that.
Yeah.
Okay, so we can use the number translation of R is discrete.
Right. Yeah.
Nabla x invertible is not the same as x invertible.
You are right. Yes.
If you apply the Nabla translation to the statement, you have.
Yeah, you are right.
Nabla.
I would have one additional nabla here, but you can prove that this is actually redundant. Okay. Yeah. For instance, I know that for a fact because of this bullet point. Yeah, the statement that x is 0 or there is an inverse to x is a geometric formula. Hence, all the nablas can be collected at the very front. Yeah. I think I would prefer to reveal that mystery of where like the subtlety is, which saves us from deducing bottom later, because I don't see it right now. I forgot. It's a very basic point, but I still forgot it right now. And I think this is how I want to conclude it. So thank you for your attention. Any further questions?
No? Okay. So if we want to formalize more synthetic algebraic geometry in ACTA, I could introduce Nabla as the inductive type, right? So the two concepts that you wrote down. And then we could do something like prove that theorem.
Yeah, exactly. Exactly. Yeah. Exactly.
And yeah, but before we do that, we have to find a name for Nabla. Because here was just generic for an arbitrary modality on positions.
But yeah,
It's subjective simplification if you have all the three clauses. Yeah.
but okay, but the reason you do this with this specific nabla and not, for example, double negation is that this corresponds to a more interesting theorem in traditional geometry, because this is actually interesting topology.
Exactly.
You don't get.
Yeah, it's more fine-grained. Also, for instance, Matthias has the following result. Every line bundle on A1 is not trivial. This corresponds to some statement in traditional algebraic geometry. Roughly speaking, that every line bundle on A1 is trivial on a dense open, but not actually dense open, because we are working with the big Zariski topos and not the small Zariski topos, so a more nuanced version of dense open. It's more something like at each closed point, there's a finite field extension and then the result holds, something like that. So Matthias recovered easier consequence of that Quillen-Suslin result. However, if you have a look at Matthias' proof, you don't actually need the full power of the double negation modality. That Nabla modality with the third clause works for his proof just fine. So actually, Matthias has proven a slightly stronger statement. Still just a weak special case of Quillen-Suslin, but also with less difficult tools. So still a nice result.
But actually, you put more, I mean, bottom. So.
So this definition, I can imagine that this number P is something minimal, that's why it's 2 dots.
Yeah, right.
And I ask myself for the concrete example of x equals 0 or x invertible, doesn't that formula itself satisfy the 2 clauses? Isn't deleting the number, isn't that already it?
It doesn't satisfy
It
the
could be.
second clause for other x.
Which other x?
So the
This
second
is
clause
one
here
clause for each x
for each
in the ring.
It was on the board before you erased it.
Yeah, but
We don't have 2 clauses,
Mhm.
we have 1 plus alternative R clauses.
Right, okay, but that's this remark that you use 5 main parts that you go.
Yeah.
Yeah, so
I can
1 plus R. Sorry.
But yes, I can extract the following remark out of this comment, namely, if nabla tilde is a modality in the sense of before, such that empty first condition, then an interesting second condition, namely R is discrete. So the nabla tilde, and then perhaps also third condition, namely that R is algebraically closed, in the sense that every monic polynomial of positive degree has a root. Yeah. If that, then for every proposition P, nabla P implies nabla tilde P. So that's exactly expresses that minimality of nabla P. Nabla is not just some random modality which renders those 2 correct. It's the minimal one. And if you know that modalities in the risky toposes correspond to subtoposes, then you also have a topic theoretical interpretation of all of that. Namely, for some results, we don't work in the Zariski topos, but in a certain subtopos of that Zariski topos. For instance, the subtopos corresponding to the surjective topos. But we don't need to be so blunt and work in that subtopos from the very beginning everywhere. We can be more careful and introduce the nabla exactly where we need it. So that most of the time we are only working Zariski locally, but sometimes when results required, we pass to the surjective topology or related. Similar, exactly as in constructive mathematics, we always have the classical connectives available in case we need them by just putting a double negation problem. But most of the time we can stay in the more positive track. Okay. Max?
Maybe one last bit about the confusion at the end.
Yeah.
I mean, is there something tricky going on with the meaning of turnstiles of I and I side? Because the interesting result is that, for example, if phi applies psi classically, then double negation translation phi applies double negation translation of psi but constructively.
Right.
So it's like
and here we have something similar, but it's not classical constructive. It's constructive plus discreteness and constructive without the assumption of discreteness. It always depends on the modality which additional axioms you may now use in your proofs or pretend to use in your proofs. And for that modality, it's this.
But so in any case, when you wrote the turnstile thing, you did not mean
yeah.
And then say this is true for all formulas phi and psi in the first order language of the ring R also.
Yeah.
And then ask that, I mean, they can also form the nabla translation.
Yeah.
But then I regard the whole thing as an internal statement. This is not true, is it?
Indeed. Let me write it down and then cross it out.
So maybe we did something like that.
I don't think that this was the issue.
Okay.
Yeah.
So this is what you were just saying, and you are correct, but this does not hold.
Yeah, so
This is really a translation on the level of proofs. If we are given a proof of that, then we can, with just a polynomial increase in the proof length, obtain a proof of that.
But if you wrote a nabla in front of the first time, then
you mean like the join
of time.
in Haskell for monads?
Yeah.
Yeah, but we still won't have the nabla. Instead, we will have a nabla to the left.
Right.
Yeah.
is the number translation always implied by phi? Does phi
No.
imply that?
No.
Okay, then maybe
We
the axioms, the basic axioms of synthetic architecture that we're using, maybe the number translation of that doesn't hold. Is that the error we made?
But that should be it, yeah.
So we assumed R is discrete, and then we used bottom, but of course we used more than the discrete thing. We
Right.
also used other things we know about R, namely the SQC axiom, and then the number translation of R is discrete just holds, but the number translation of the SQC axiom probably doesn't hold.
Yeah, it's that, and I checked. So a couple months ago, I checked which one exactly was the problem, and I don't recall that. And we need to do that again.
Okay, so but which axioms are we allowed to use then?
Definitely all those axioms which can be, and also all results or consequences of the axioms, which can be put as geometric sequence.
Yeah, but
Because we know that if a geometric sequence holds at the top of, then it remains true in all subtops.
Yeah. But you promised that the Doubler translation, that this makes things easy and we can work naively with it. So and we try to naively use the axioms and ended up with the bottom. So okay, now we can use geometric consequences of the axioms, which makes things again complicated. So
you mean because we need to keep track which things are geometric sequence and which are
so which comes so is there a is there a simpler way to state our
no, I don't think so. But I also think so it's a valid desire to have it, but I think that desire is not fulfillable. But I also want to mention that this final bullet point with the translation is just like some bonus, some nice thing to have, which works in some situations, so that in case we master that bit of logic, we can more quickly deduce results. But it's not the core message. The core message is that we have the modality itself, not the translation, just the modality, and that we can and need to use it where needed.
Okay, but we can use one more message. I mean, we can take our SAG axioms, our axiom schemes. Then we try to derive as many as possible or sensible true statements that are hold under this modality. And then we have a new set of axioms, namely SAG nabla. In SAG nabla, R is in fact a field, a discrete field. And then we know that then we have a meta theorem saying, well, everything that holds in SAG also holds in SAG prime. And everything that holds in SAG prime holds in S nabla locally. No, sorry, that was that's wrong. I have to restrict the geometric formulas.
But I like what you're saying. This is possible,
so let's try to find good axioms for SAG prime.
Yeah, there's one catch, namely there's one important axiom which will definitely whose NABLA translation will definitely not hold, definitely not, and that is the risky local choice. Because the risky the reason the risky local choice is an internal reification of the topology used to build the big risky topos, which is the risky topology. However, with the NABLA, we are now working in a subtopos of the risky topos, namely possibility convergence to a technical topology. Hence, we cannot expect the risky local choice to hold. Instead, we will have subjective local choice then. Yeah? And this complicates a couple of proofs because now they need to deal with more coverings than before. It's easier to verify a local statement, but it's harder to use a local statement. Right? Which is one reason why I think I advocate for never use or trying to never use the risky local choice in the basic development. Instead, in the basic development, always using FPPF local choice, because it's a weaker choice principle. It just tells us the existence of an FPPF covering instead of a risky covering. So if we manage to do our proofs with that weaker choice existence, then in particular it holds in the standard flavor of synthetic algebraic geometry, but then also it holds in more advanced flavors. And it turns out that for many results for which we use the risky local choice, in fact, the FPPF choice would work just as well. In the moment where we are at the blackboard and we are using it, like after the fact, we always need to enter the proof again. But while we are doing it, it's positive.
The situation with this NABLA is a bit different because the base ring is not modeled for this NABLA.
Yes, that is the difference, right? Exactly.
So I guess SQC break as well. I'm not sure you can.
That's the reason why SQC breaks. So I was confused because the SQC already holds in the pre-sheaf topos,
right.
where we didn't even force the R to be a local ring. But then it still holds when we force it to be a local ring, and it's thought for a moment it holds in all subtoposes.
But no, that's not true.
Maybe it's
exactly that. The structure sheaf of the pre-sheaf topos, so R, happens to be a sheaf for the Zariski.
Yeah, right.
And it also happens to be a sheaf for the FPPF, but it is not a sheaf for the NABLA.
Okay, and for you, that's also the reason why SQC fails in that.
Yeah, but I seem to recall that I had a good enough replacement for SQC, not for the risk local choice. For that, we just don't have exactly a simple replacement that we have NABLA local choice. But for SQC, I seem to remember that
something that does not imply bottom together with R is interesting.